Come on in, everyone. Come on in. I'm in the process of trying to get my notebook open for my iPad so I can write easier with you guys. And that did not work. So I'm still loading that up. We still got a few people coming in. Now's the time where you can ask me questions if you like while we're waiting for everybody to come in. I am just typing up some stuff. So when you go to Google Docs, it'll actually have the right name on it. Does anyone have any questions before we get started? And happy Halloween, everyone. All right, now I've got it. Okay. Looks like we got 10 of you in here. That's not the whole class, but I don't even know if we had Halloween here in North Carolina in my neighborhoods yet or not. We were gone Friday night and Saturday night for a funeral, and still have some stuff to take care of with regards to that. But anyways, anybody haven't, I guess no one has any questions because you haven't asked any yet, but I am here to begin helping you guys with this next chapter. If I remember correctly, let me look at my notes just to double check. If I remember correctly, the last thing I did in 241 was, oh, that was some problems. I was working for homework. Not really the same thing. Oh, we finished up conservation of momentum and did center of mass, and I hinted or advised you that I had made some videos that you should check out on my YouTube channel. So definitely check that out. www.youtube.com/physics with a capital P solutions with a capital S on the front, Billy capital B on the front, and Younger capital Y. So that's the name, but yeah, check that out. There was two specifically regarding train cars where I'm actually solving the same problem twice, but in one case I'm doing it with conservation of momentum, and the other case I'm doing it with center of mass. It's just a really cool problem. I found out when I was teaching. It was like one of the first problems I ran into when I was teaching it. It was fun to do, but it wasn't trivial. The first time you ever see it, it's not a trivial problem to solve. I think that's when it might have been when I was teaching as a grad student, in fact, that I had ran into it, but it was a little bit tough initially, but I loved having it. So I wanted y'all to see an example of it. So does anybody have any questions about anything? If not, I guess we're going to move on. All right, first thing I'm going to do is I want to open up my lab and mastering so we can turn to the chapter that's relevant. So I'm going to share my screen with you guys, and I have another screen to share. Of course, it's the screen where I'll have my iPad on it, but right now I'm trying to navigate to the book slowly, very, very slowly. Still only have, what, 11 people in here? It's not, yeah, I think we have 11 now. Man, this is moving slow. Oh, there it is. We got speed now. Woohoo! Man, we should start meeting like this, like even in the classroom, just because like all your faces have names associated with them, and I can finally, for once in my life, call my students like I know who they are. I'm so horrible at this. Speaking of which, I watched Bullet Train last night, and Brad Pitt made a comment about that, and it kind of cracked me up because, you know, in reality he has, I think it's called parapagnosia, which is where you can't remember faces very well, or I might be mistaken it with this other really rare malady, but that name anyways. But anyways, he does have that problem in reality. He can't recognize faces, and I can recognize faces. I just can't get my brain to associate that with a name for any extended period of time. It's a gift, really. All right, I'm trying to open up the e-text and see what's going to happen. So we'll see how that works out. It seems to just sit there. Oh, ooh, we're on our way now. There we are. I was doing it with my iPad. That's why I don't have it ready yet. But the iPad was going even slower. So I said, oh, I'll just do it with my Canvas. That didn't, that was not a good idea. Jumping ship midstream did not help. We're on it now. Okay, so that helps. That's chapter 30, which is what I finished in the 242 last time. So what we have to do now is chapter 10, which is rotational motion. So I wanted to explain that to you. And the neat part about rotational motion is all the equations from rotational motion look just like the equations that we have from linear motion. Specifically, if you go back to kinematics, you're going to find very, very similar equations. So for instance, our equations in kinematics were stuff of the form of, let's say, V equals dx dt. Well, there's a corresponding analogous equation for rotational motion, and instead of V, we use the symbol omega. And omega is actually equal to, instead of x, we actually use a theta, which corresponds to an angle. So omega is an angular speed, often measured in radians per second, and that's the unit that always works. And theta is a unit of angular measure, and that's normally measured in radians. That's the unit that always works, but a lot of them occasionally work. Others units also work. But in other words, omega would be equal to d theta over dt, just like v is equal to dx over dt. Similarly, a was equal to dv over dt. Well, in angular motion, we have alpha is equal to d omega over dt is another equation. F equals ma, we have something analogous to force, or the summation of the forces on the left-hand side of Newton's second law. We have replacing that the summation of the torques, and we just arbitrarily say, torques that cause clockwise rotation are negative and torques that cause counterclockwise rotation are positive, or whatever system we want to use is fine. But we'd say the summation of the torques, which is implemented by the symbol tau, is equal to something equivalent to mass, which turns out to be the moment of inertia. That's what we call it in physics. It's called something different in statics and dynamics. Well, actually not in statics, but in dynamics, they call it something else, and they call it something else also in strength of materials. But we use the symbol I. I think you guys call it, if I remember correctly, I would just call it a moment, but it's the moment of inertia, and it's basically if you add up the individual mass particles from some in some system, and you multiply each of those masses times the square of the distance they are away from the central axis of rotation, and then sum up all those MR squares, then you get the moment of inertia. And you can see now that moment of inertia depends not only on mass, but on the distance it is away from the center of rotation. And of course, it actually depends more strongly on that, so that if you double the distance away, you quadruple this moment of inertia. So it's actually a quantity that gives you a real feel for what it takes to rotate something. So you might think, well, there's no difference in these two tires, for instance, that I've got on my truck. Let's say even if the weird case where 30-inch tires have the same weight as a 31-inch tire, because maybe made the side profile smaller on the 31 or 32-inch tire, right? But it turns out even if they were the same weight, it would still take more energy to rotate those tires, because the moment of inertia has gotten larger, because the radius has gotten larger. And in fact, it's much bigger effect than you expect, because going from 30 to say 32 is a difference of not 32 over 30, but 32 over 30 squared. So That's some of the ideas that we're going to cover here. What I want to do is now show you some of these equations. The first one normally is from your trig class where you first learned about radians, and that is S equals R times theta, or in this case, your book is using L is equal to R times theta, but they've got it solved for theta. So L over R is equal to theta. Notice that theta is actually supposed to be measured in radians, not radials, as this new version of the textbook has a typo in it already. So it's radians. But notice it's a length divided by a radius. So that, in fact, could be centimeters over centimeters or kilometers over kilometers. In fact, it doesn't matter what formula you or what units you use, as long as you use the same for both of them, and the radian will automatically come out because the radian is just a pure number. It has no units. It's a non-denominate number is another way of saying it. So if you look at equation 10(1)b as shown here, you've got S equals R times theta, or in this case, like I said, L equals R times theta. That's it solved in a normal form. And when we realize, wait a second, that L is an arc length for any angle theta, if we go completely around, we know that that arc length is actually something called, anybody remember what that's called when you go completely around a circle and measure the length around it? It's not perimeter. What's that distance around a circle called?
Circumference.
Circumference, exactly. So that's where we get the form. If you take the formula circumference equals 2 pi r, then you see, oh, well, that explains why we get 2 pi for 360 degrees. 2 pi radians is 360 degrees. So that's kind of helpful. We also can use the conversions that 1 revolution is 360 degrees, but that's also 2 pi radians, which you could also say that's 180 degrees is equal to pi radians. Or you can say 57.3 degrees is approximately 1 radian. So those are very typical numbers we use. Some interesting things to do is calculate through how many radians does a second hand move in, let's say, 15 seconds. Okay, that's a neat problem to consider. So let's do that now. We have this set up. I'm going to share my iPad screen. So let's do share screen, iPad, and about once every 10 times I go to share my iPad, it makes me install an app that I've already installed, but lucky it didn't do it this time. Okay, so there's my iPad screen. And so I'm asking you, let's look at the face of a clock. And for some reason, all of a sudden, my writing tools have become disabled. There we go. See if it comes now. Nope, that's not it. Let's try opening this guy again. Why is it not letting me write anything all of a sudden? All right, some of you got, oh, there it is. Okay, got it. my actual menu disappeared, so that I'm going to say that's on me. So let's do this. Let's draw a face of a clock. Well, good. Y'all see how good I drew that circle? Wow, that was awesome, wasn't it? So anyways, on the face of the circle, we have the 12 o'clock slot. Okay, and clockwise, of course, means the top goes to the right. So over here should be the 3 o'clock slot. And this is 12. And what we asked is how far the second hand moves in 15 seconds. So we know, for instance, that the second hand, which looks like this, will move from here to here in 15 seconds. So what we say is the angular measure of displacement is theta. And in this case, it turns out to be 45 degrees in 50 seconds. Is that correct?
The 3 would represent 15 minutes, right?
Right.
And you were saying 15 seconds?
Right.
So
You're right. Go ahead.
Okay, let me think about it.
So no, you're right. Go ahead. Is there something wrong with what I wrote? Yeah, it is. It's wrong. Okay. Actually, this is one of the few times where I made a mistake on purpose. Okay. But it's very normal mistake. Specifically, it's not 15, or excuse me, it's not 45 seconds from or 45 degrees from there. That's clearly 90 degrees, right? But it's 45 seconds. So this is, like I said, one of the few times where I made a boo-boo, sort of on purpose. I actually almost made it in my head, and then I said, "Wait, correction." And I said, "Wait a second, let's go ahead and write that." So, anyways, here goes this. So it actually goes 90 degrees in 15 seconds. Okay. So what is that in radians? Well, we can do like this. We can say theta equals 90 degrees. And then we can say times, we know that you can either do 180 degrees is equal to pi radians, in which case you see that's pi over 2. But you could also do 90 degrees times 2 pi radians and 360 degrees. And of course, this would be 2 pi. Whoa. I don't know if y'all knew this, but the 4 is often written as a pi. No, it's not at all. I made that up too. So 2 pi over 4 radians, which again gives us the same answer of pi over 2 radians. Okay, or you could also do 90 degrees times 1 radian is about 57.3 degrees. And that just turns out to be horrible because 90 divided by 57.3, no one likes to calculate, but I'm going to do it anyways. But you can probably guess it's somewhere close to half of 3.14159, right? So let's see. 90 divided by 57.3 is equal to 1.571. And of course, pi over 2 is about 3.14159 over 2. So that'd be 1.5 plus 0.07. So it's 1.57 plus 0.0005. So 1.75701, something like that. So yeah, that's pretty close. No, actually it does end up in, no, it doesn't end up in one place. It ends up in the next place over. So that'd be 0 and then a 1, something like that. But actually, if you take it to 16, it'd be 0, 0, and an 8. So that's pretty close. So everybody gets that. Now, what would the angular speed of the second hand be? So let's go back to black. What is the angular speed oh, forgot how to be on average of a second hand in, let's say, cycles per second, cycles per minute, radians per second. Okay. So we know that the equation that we used to use.
Professor?
Yes, sir.
Sorry, I had a question. So in the first example, does the radians, does that represent the arc length?
So the radians is actually the angular measure. It's equivalent to degrees. But if you wanted the arc length, if you wanted the distance, say, from here to here along this curve, we could call that distance L. And if I knew the radius, say, from here to here, what I would do is take that pi over 2 radians and multiply that by the r, and that would give me the arc length. So if r equals, let's say, 0.50 meters, so it's a pretty good sized clock, right? Then L would equal 0.50 meters times, and this is the case where you only can use radians. Okay, so that's times pi over 2. And you'd see that is about 0.25 pi meters. So a quarter of pi, which would be about 0.7735 maybe. So 7735. Okay, so that's the arc length. And again, it has to be done in radians, one, because radians is actually a pure number. So if you multiply meters by anything other than a pure number, you're going to get some measurement other than meters. So it has to be in radians for that reason. But the other reason is this equation is only valid. The L equals R times theta is only valid. And we normally knew it like this from trig. It's only valid for theta in radians.
Okay, thank you.
No problem. All right, so now what I'm asking is what's the angular speed on average of a second hand in cycles per second, cycles per minute, and radians per second. And what I'm saying is I'm going to try to reason by analogy to figure out exactly what the answer to this equation is. So I know that when I was dealing with linear motion, I knew that the average velocity v was equal to delta x over delta t. I also know that omega is analogous, say, to v, and I know that theta is analogous to x. So I'm going to guess, and I'm saying I'm guessing, I actually know the right answer, but as a student that had never seen this before, I could actually make this guess. I could say, okay, well, I think the average angular velocity is equal to theta over t, or theta minus theta 0 over t minus t0, because time is going to be the same in either one, which is, of course, more equivalent to what I actually said, which is delta theta over delta t. Okay, so I could probably go straight from the left-hand side at equal to the far right-hand side, straight from analogy, but for some reason I wrote it the other way around because I'm a horrible teacher. I'm a learning teacher and I'm trying to do better, but evidently that was just a stupid thing for me to do. And I got no other way to admit that. So does this seem like a reasonable equation for the average angular speed? Omega equals change in theta over change in time. Does that seem reasonable to everyone? So that was my hypothesis. And it turned out it was right, by the way. So let's do the solution. Nobody's answering me. I'm hoping y'all are all getting this, but please stop me if you're not. This is actually a fairly easy equation, chapter if you learn the basics. And I'm getting through the basics now. So we're going to say omega average is equal to delta theta over delta t. We just concluded that delta theta, or just plain theta, because we could call theta 0 to be 0. We could do that, for instance. In that case, we're just going to get in cycles per second, we're going to say that this is one cycle. Or actually, let's take the data we already have instead of making it instead of trying to work it out the way that's sort of obvious and reasonable. Let's make sure that the less obvious and less reasonable gives us an answer that's reasonable. So what we know is a cycle, you know, period where something starts and then starts repeating itself. So if we look at a cycle for a second hand, that could be it starting at the 12 and then reaching what again?
12.
12, exactly. And that's a full cycle, right? 12 all the way around to 12. So what fraction of a cycle is 12 to 3? What fraction of a cycle is from second hand going from 12 to 3? Through what kind of angle or through how many cycles?
A quarter.
A quarter, yes. So we're going to say delta theta is 1/4 of a cycle. Now, does anybody recall how long a whole cycle would take for a second hand? It's going to go from 12 all the way around to 12. Now, this might be hard because I know most people grew up on digital watches and haven't had much experience with the second hand, but those two little digits past the minutes, that's what the seconds are doing. Do y'all recall what the little digits after the second, after the minutes counts up to before it goes to another minute? Anyone? So in seconds, when the second hand goes one click to the right, that's 1 second, 2 seconds, 3. So there's 45 seconds, for instance, or excuse me. There's 15 seconds. There I go again. There's 15 seconds in that one cycle. So 15, 30, 45, 60 gets the whole way around. But a quarter cycle is 15 seconds. So I'm going to say a quarter cycle per 15 seconds is the number of cycles per second. And of course, that's one cycle per 60 seconds. And that's what I mean by we were going to do the less obvious way and see that the answer makes obvious sense when we did it right. So yes, we should know that a second hand takes 60 seconds to complete one cycle, and that's basically what the angular velocity is. It's one cycle per 60 seconds. How about omega prime, or excuse me, omega average in cycles per minute? What do we get from that? Okay, it's going to be one cycle, right? One cycle. How long does one cycle take in minutes?
1.
Exactly. So this one's easy enough to say 1 cycle per minute. Okay. Now, by the way, this 1 cycle per second is also equivalent to 1 hertz, believe it or not. So we can actually use that as well. 1 hertz. It's not nice to do that because, so let me put a little approximately question mark, because in reality, what you really want is omega to be equal to 2 pi times something called the frequency. So it is equivalent to it, but I just don't want you to get confused because often we'll use omega for the thing that's measured in radians per second. So that's usually in radians per second, in which case you take this, which is measured in hertz, and you would call that 1 hertz is equal to 2 pi radians per second, which I think you can see because we're going to ask now, what is omega in radians per second? That's delta theta over delta t. So the 1 hertz is correct. I just don't want you to confuse that with the F symbol that it really should be called by. So how many radians does a second hand pass when it goes from 12 to 12?
2 pi.
2 pi radians. And how long did that take in seconds? I'm glad some of y'all are answering. Come on, guys. Guys and gals, ladies and men, dudes and dudettes.
There are responses in the chat as well.
Are they? Maybe that's it. Okay, sorry about that. Hey, yeah, I see a number 5 down there. Thank you, guys. Y'all been doing all this, and I'm just a cracky. I didn't notice it, so I apologize. Yes, so it's actually in 60 seconds. So this is in fact 2 pi over 60 radians per second, which you can probably recognize 2 divided by 60 would be 1/30th. So it's pi over 30 radians per second. So let's ask another question. This will help us better with our radian figures. So how many radians let's say, I don't want to say A, does the second hand traverse in 5 seconds? Anybody have any idea on that one? That was a horrible, supposed to be a circle, but that did not go well. It changed it all by itself to a half circle, which is what I was shooting for, but it changed it to a half parabola. So I wanted to draw a whole circle. Okay, so I'm going to go from here, for instance, to here. That, of course, is supposed to be pi over 2 radians. And then, of course, that's also 45 seconds. And then, of course, this is 30. Ooh, that's 15 seconds. Excuse me. God, why do I keep doing that? I have no idea. Mixing 45 and 15 up for some ungodly reason. So that's 15 seconds. Sorry. And then, of course, this would be 10 seconds, which is obviously 2/3 of 15 seconds, which is obviously therefore 2/3 of pi over 2. So that would be pi over 3. Okay. And then this one right here would be the equivalent of 5 seconds. And that made that a lowercase delta for some reason. Actually, I know exactly why, but it was my handwriting. Now that's, of course, 1/3 of 15 seconds, and 1/3 of 15 seconds would be pi over 6. So that's pi over 6 is the number of radians the second hand traverses in 5 seconds. Any questions on that? So theta for 5.00 seconds on the second hand is equal to pi over 6 radians. What's it in degrees? Anybody know what that would be? I said it a second ago, but it'll help you to remember that it's a third of the 15 seconds. So
15 degrees.
15 degrees, very good. So it's good to refresh yourself on radians. This is the one chapter where you'll kind of use it a lot. Another chapter will be when we get into AC circuits, and another chapter is when we get into pendulums and maybe mass on a spring to some extent, but mainly in the electricity portion of the AC circuits, you'll run into radians again, and with waves. There might be some instant with there. So with that, so there you go. That's some ideas of what theta is. Now let's look at some other examples. So for instance, we knew from linear motion, we knew that V average was equal to delta x over delta t. And then we found that V instantaneous, or actually, I guess I did like it better with the S there. The instantaneous was basically equal to the limit as delta t approached 0 of delta x over delta t. It's really some of the worst writing I've ever done in my life, which is essentially dx over dt, right? So we've already found that the analog to this first equation was omega bar is equal to delta theta over delta t. And that turned out to be right. But now we can also say that this should imply omega instantaneous is equal to d theta over dt. And that turns out to be right as well. Okay, so this is a check mark, everybody. You can also go a little bit further and say that, well, given that that's the case, we also said x is equal to x0 plus v, whoa, that's not a v, plus v bar t. That should be analogous to theta equals theta 0 plus omega bar t. And that's correct as well. And notice that's just a reconfiguring, if you will, of the first equation. I'll call it A because that was in linear motion, and I'll call the second equation B, right? So this is 1 and this is 2, where A is the same as 1 and B is the same as 2. This is A, and this is equivalent to 1 because it's the same equation, theta minus theta 0 equals over delta t is equal to omega bar. So that's kind of nice. We also found that A, the average acceleration, was delta v over delta t. And from that, we found that the instantaneous acceleration was the limit as delta t approached 0 of delta v over delta t. Well, that could be, for instance, equation C and equation D. And of course, that gave us equation 3, which is alpha bar is equal to d omega over, excuse me, I shouldn't write d omega, is equal to delta omega over delta t. And that suggests that alpha is equal to the limit as delta t approaches 0 of delta omega over delta t, which is d omega over dt, and that's equation 4. And that one also turns out to be correct. So does that make sense to everyone?
we also had this weird case where it turned out another way we could calculate the average velocity if the acceleration is constant, then V bar is just V1 plus V2 divided by 2.
Okay, that's an equation we very rarely use, but sometimes you use it and it can save you a lot of steps. In fact, in the algebra-based physics course, they use this to come up with the other equations that we use or that we found using the calculus. So for instance, the x equals 1/2 at squared plus v0t plus x0. If you substitute that in for v, if you substitute that v bar in there using this formula for the x equals x0 plus vt thing, then that can actually allow you to determine that equation, x equals 1/2 at squared, blah, blah, blah. And it also can allow you to get v squared is equal to v0 squared plus 2 alpha x or 2ax or 2a parentheses x minus x0. So this is going to be called equation E. And it turns out that omega bar is in fact equal to omega 1 plus omega 2 over 2 if alpha equals a constant. Okay, and I wrote that E in the wrong place. I'll just put it here. Okay, so actually I shouldn't put it there because I actually did write it in the right place. I just put it in the wrong part of the same line, of the right line. So this is actually going to be equation 5. And that is one true. And in fact, I've never used this for the rotational motion. It might just be that I haven't solved as many rotational motion problems. I just can't recall ever using this for rotational motion. But for completeness, I wanted to show you that it works, and there's good reason for it to work. But now, if we actually use either that or we use the idea that acceleration is equal to constant, then equation 6 would be x is equal to 1/2. That's not equation 6. That's equation F, because I'm using letters for the linear equations. So F is x is equal to 1/2 a t squared plus v0 t plus x0. Well, the analog to that is, of course, equation 6, which is theta equals 1/2 alpha t squared plus omega 0 t plus theta 0. And of course, if you solve this equation for t and then plug it into, if you solve equation, let's see, if you solve equation 3, so solve equation 3, actually I should make it bigger than that, for t, actually I should use equation 4 too instead of equation 3 because that's the average one. Whoa, that was not an eraser. Okay, so equation 4, oh good, my eraser just stays. So solve equation 4 for t and plug it in. Six, you get this equation here, which by the way, we know of as equation G, v squared is equal to v0 squared plus 2a x minus x0. The analog, of course, to that is omega squared is equal to omega final squared. Whoa, not a final, where did I come up with that? Omega 0 squared plus 2 alpha theta minus theta 0. And that turns out to be equation 7. Okay. And you can sort of see this by, let's take our L equals R times theta. And let's talk about purely circular rotational motion. So that means R is a constant.
So you can see all this to be true by considering this. And let's, instead of calling that L, let's call that X, or is equal to R times theta. Then you can see that dx dt is equal to R d theta dt. And that's a new equation. In fact, that's going to be equation 8. And it says that V is equal to R times omega. That is now an equation that converts us back and forth between linear motion and rotational motion. Now, if you take the derivative of that equation, dv over dt is equal to R times d omega over dt. Again, remember the R is a constant. Then you get A is equal to R times omega, which is yet another equation that is useful because it converts again back and forth between, oh, I said A, excuse me. That was not supposed to be an omega on this side. Everybody, does anybody not know what should be there? I know nobody said anything, but you might have typed it out. I did not see it in the chat yet. But does anybody know what was supposed to be there instead of omega? It's a good chance to learn from my mistake.
V.
Close. You're thinking along the right lines because you're remembering that I wrote omega, and you're thinking, oh, the linear equivalent of that is V, which is correct, but we're trying to relate to the rotational equivalent of A. What symbol is the rotational equivalent of A? Anyone? It's okay. It's, this is the first time you've been exposed to it, so it's, you know, not unreasonable for you not to know. I was just figuring y'all might because y'all are so smart in general.
Is it alpha?
It is alpha, yes. Okay, so that's the actual equation. So if you take those two equations, 8 and 9, you can see something kind of interesting. For instance, when you say x is equal to 1/2 a t squared plus v0 times t plus theta 0, or excuse me, plus x0. You can say, wait a second, this is r times theta is equal to 1/2 r times alpha times t squared plus r times omega 0 times t plus r times theta 0. Notice the r cancels out and all of that. And lo and behold, you get the theta equals 1/2 alpha t squared plus omega 0 t plus theta 0. So that's just another way of thinking about how these equations came to be. Any questions on that?
I put a question in the chat.
Yes. Oh, there it is. My chat isn't automatically scrolling up, so I'm just like, nobody's put any new chats up there. In the derivation of equation 8, did we say that omega equals d theta over dt? Yes, that's correct. Omega is d theta over dt, and alpha is d omega over dt. Now, you guys remember this when we covered when we were in Newton's second law, we found that A is equal to V squared over R. Do you remember that? Anybody remember what kind of acceleration that was called?
I think that was
Centrifugal.
centrifugal.
Yes, very good. Centripetal acceleration. Now, that was rotational motion, wasn't it? We were talking about things going in circles, weren't we? So I want to bring that to your attention to realize, hey, wait a second, there's acceleration, right? There's acceleration that we talk about, and I'll call that A, and it's actually a vector quantity. But in fact, what it is if you switch to the right coordinate system, there's a tangential vector, and then there's a radial vector, And then what you'd say is that A has a tangential acceleration alpha that if you multiply by R gives you the direction that's tangential. So I'm going to say T hat, just to remind you it's tangential. And of course, the hat tells us that it's a unit vector. Plus, and notice if the R wasn't there, I would have the units of radians per second, and we need radians we don't need radians per second, we need meters per second. And then there's also this other one that is A sub C, which is what I should have subscripted that with just to make sure y'all knew, but I will do it now. And that is in the, actually, I should put that in the negative R hat direction. So R hat would be radial. So this is tangential. And this is radially outward. In case you don't recognize that word, I suspect most people do, but radial sounds like radius. And when we say radial, we generally mean the radius direction, the direction of the radius, but from the center outward. So that's what I mean by radially outward. And by me putting that negative in there, that reminds you that actually the centripetal acceleration that I gave up above had to be a negative for it to go in a circle. In general, that quantity can be positive or negative, but if I'm using v squared over r, then it should be generally negative because that's the centripetal acceleration you have to have directed radially inward to maintain a circular orbit. So I wanted to let you know there is yet another connection in addition to v equals r omega and a equals r times alpha. There's this third relationship, a, which equals technically r alpha t hat plus, and now I'm just going to say a c r hat because that's the general centripetal acceleration that it might have. And actually, I shouldn't even say centripetal, just because if I said centripetal, then that would imply inward. And I don't want to say that because centripetal means center seeking. And what I want is A sub R for radial. That's probably the better way of writing it. So that was equation 8. That was equation 9. And this is equation 10. Okay. So all those problems we've done with kinematics, like, an object starts off at the origin and has an initial speed of 20 meters per second and an acceleration of 3 meters per second. How far will it have traveled in 2 seconds? That's the x equals 1/2 at squared plus v0t plus x0 equation. Well, I can do the same thing. I can say an object starts at theta equals 0 degrees with an initial angular speed of 20 radians per second and an angular acceleration of positive 2 radians per second. Through what angle will it have turned after 3 seconds or after 2 seconds? That's the exact same problem. So let's try that just to give you an idea. So, and I'm going to do just the angular one now. An object at theta equals 0 radians. Now, all these equations, by the way, work with radians, but most of them work even without radians, not the v equals r omega, not the a equals r alpha, but a lot of them will actually work anyways with other units. You just got to check and see, do the units cancel out like they're supposed to? So an object at theta equals 0 initially has a speed, I should say angular speed, even though the units would be enough to tell you, of, whoa, I went cursive on that, of 20.0 radians per second. And has an acceleration of 2.00 radians per second through what angle will it have turned in 2.00 seconds, in 3.00 seconds, since I've sort of quibbled a bit about which one I was going to use. And then I'll also say, what will be its final angular speed in each case. Okay, so let's do solution again. Anybody have an idea what we're going to do for the first part? Notice if you change the units and the wording to get rid of the radians and radians per second and replace it with like meters and meters per second and stuff like that, the equation you use from chapter 2 or 3, whichever one it was, is the exact same equation you use here, but in the analogy, the analogous one. So if you're having any difficulties, you can always think that way. So anybody have any idea what equation we want to use for the first part, where we're wanting to find out through what angle it's turned in 2 seconds? Checking my chats. Nothing. So this is going to use theta equals 1/2 alpha t squared plus omega 0 t plus theta 0. Now what they're telling you here is theta 0 is 0. But what they're really asking you for, because I say through what angle will it have turned, I'm really asking for delta theta for t equals 2.00 seconds is equal to question mark. So I'm really asking for, this is a little bit, weird, but I'm really asking for delta theta, which is theta minus theta 0, which is equal to 1/2 2.00 radians per second every second times 2.00 seconds squared plus 20.0 radians per second times 2.00 seconds. So that's what we're calculating. Now, what I would tell my students in conceptual physics, and this is a good thing to do now, we're doing rotational motion. So I think it's pretty obvious in the linear case, even though I didn't cover it there. It's a little less obvious here. So I think it's good to discuss the kinematics of what's going on here. What the heck did I just do? I think I just erased everything. Nope, I switched to a different one. Ooh, that was scary. Nope, switched to that one. There, I just thought I lost everything. That was a terror. Okay, so when you talk about motion, there's motion that you have as associated with a constant velocity, and there's motion that you have associated with a acceleration, and then there's motion that has both. Well, in this case, and in all cases really where you have both, you can think of what would the object do as a first order shot over the bow if it was really moving at constant speed. Well, if it was really moving at constant speed of 20 radians per second, in 2 seconds, you'd expect it to go 20 times 2 or 4 radians, or excuse me, 40 radians. And that's exactly right if it was constant speed. But what we've learned here is that its acceleration is in fact 2 radians per second every second. So we know that the displacement is proportional to the time squared. So in 1 second, it'd be 1/2 times 2, which is 1 radian per second, times 1 times 1. That's going to give you just 1 radian that's going to do in 1 second. If I go 2 seconds, which is twice as long, it's going to go
times as much because it goes like time squared. So instead of going 1 meter over 1 second, and then 2 radians over 2 seconds, or 1 radian over 1 second, it goes 1 radian in 1 second. By acceleration, it's going to have to go 4 radians in 2 seconds because it goes like the time squared. So in fact, we should get an answer of 4 radians per second plus 40 radian, or excuse me, 4 radians plus 20, or excuse me, 40 radians per second. Boy, that was really badly said. The main thing is what I'm talking about is that first term on the that I was discussing was the far right term, the 20 radians per second times 2 seconds. That's linear in time. So you expect it to go 20 radians in 1 second, 40 radians in 2, 60 radians in 3, because it's proportional. But that other term I talked about second, which is the first term, that's 1/2 alpha t squared. So you expect that to go like time squared. So if it goes 1 radian in 1 second, it's going to go 4 radians in 2 seconds. It's going to go 9 radians in 3 seconds. It's going to go 16 radians in 4 seconds, so on and so forth. So with this one, I actually get, and you can do the math to see, but it's clearly going to be 4.00 radians plus, and notice the radians per second with seconds per second times second squared does actually cancel out. And this one over here gives me 40.0 radians. So the answer is in fact 44. Actually, I should put 0.0. Radians. Okay. Now I can use the same thing for the second part. This is delta theta for t equals 3.00 seconds. And that's sort of the usefulness of the part I was just telling you. I know that in 1 second, the acceleration caused 1 radian and the velocity caused 40. So in 3 seconds, wait a second, I don't want to put it there. So in 3 seconds, the alpha should cause 3 squared, which is 9 radians, and the v should cause 20 times 3, which is 60 radians. So I suspect this answer is going to be 69 radians. And that's just understanding what kinematics teaches us. Okay, again, I didn't cover these conceptual details in the linear part, mainly because I was just trying to get you through the math. And secondly, because that was pretty straightforward, I thought, but it's always good to go back and look. Now if we do the actual math, we're going to get 1/2 2.00. I'll just write that as a r per second times 3.00 seconds squared plus 20.0 radians per second. Again, I'm just using the r instead of the radians because I'm lazy. And times 3.00 seconds. And you can see that this 1/2 times 2 cancels out, and I'm just left with a 9 radians. And obviously that's carried to 3 sig figs, should technically be 9.00 radians. Now this one's also 3 sig figs, but of course this turns out to be 60. And since it's 3 sig figs, it only has 1 decimal place. So we have to round it to the smallest number of decimal places. That's why I got 69.0 radians. Okay. So that's actually right. Well, our conceptual technique of looking at the motion as proportional to the square of the time when it's accelerated, and then looking at the separate motion as proportional to the time when it's a constant velocity, and then realizing I can solve every type of problem that way just by acknowledging whether A is 0 or A is not 0 or A is negative. A is negative means you're going to subtract from that. So for instance, if that acceleration was negative, I know that I would go under 20 radians per second as initial speed. I'd go 20 radians and then 40 radians and 60 radians and then 80 radians. But at 1 second, I would lose 1 radian for each second. So at 2 seconds, I should lose 4. And at 3 seconds, I should lose 9. And at 4 seconds, I should lose 16. So in fact, if I'm doing 20 radians per second, in the second, I should go 40 radians total. But because of the acceleration, I'm going to have to subtract 4 from that, and that'll give me 16 radians. So that's how you could actually calculate that if the acceleration happened to be negative. So it's pretty straightforward. Now, the other part was we want to know what the final angular speed is. And there's a couple ways you could do it. You could say, for instance, omega is equal to omega 0 plus alpha t. Notice that's one of the equations that I didn't include. I could have. I sort of did when I said A average is equal to delta omega over delta t. That's the same equation. So I did cover it in that sense. I just didn't solve it this way. So I can use that if I wanted to. And I could say, for instance, that 20 radians per second plus 2 radians per second times, and that's 2.00. I'll put that in there just to, and there should be a 0.0 there as well, times 2.00 seconds. That should give me 2 times 2 is 4. So that gives me 24.0 radians per second is my final speed. But I could have also used omega squared is equal to omega 0 squared plus 2a theta minus theta 0. Now, I wouldn't recommend using this one because you'd have to calculate theta minus theta 0, which we did in part 1. But if I had made a mistake in part 1, then I'd now have a mistake in part 2 that a less than studious or a less than studious grader would not catch. And therefore, you get 0 credit on the whole problem or marked off on all parts of the problem. Whereas a more studious instructor would say, hey, wait a second, they did the second part right. They were using the answers from the first part, and that was wrong. So I'd give full credit in the second part. But when we do this, we would get omega is equal to the square root of, this is 20 squared, so that's 40.0 meters per second, or excuse me, meters. What am I thinking? That's radians squared per second squared. Remember, radians not really a unit, so we can ditch and add that as we need. And I love how this thing just randomly switches to erasing. Makes me want to punch a baby. Oh, they did it again. A lot of babies being punched in my life. Not really, obviously. So now I'm on this plus 2 times 2.00 radians per second. And now I'm multiplying that by the first case, which was 24, wasn't that it? No, it's 44. Times 44.0 radians. Oh, that's just plain radians. Okay, so if I take the square root of all that, that's the square root of 44 plus 44 is 88. Boy, that's an ugly crap right there. I'm going to assume that turns out to be 69. No, is that what? No, that's not what I got for it. It's 24 is what I'm going to assume that is. So I'll say 40 squared plus 2 times 44. That's 178.467. Now I'll take the square root of that. Whoa, we'll get something entirely different. That was 20 radians per second. That's what I had before. And then 2 radians per second times 2 seconds is 4. So 24. What did I do wrong here? 20 squared is, oh, duh, that's what I did wrong. Notice, everybody, that the smart person will learn that your teacher doesn't always work things out properly. And it turns out that 20 squared is not 40, but rather 400, which makes a slight difference, you know? So let's see this now. Let's say, I'm going to say 20 squared plus 2 times 2
times 44. That gives me 576. The square root of 576. And of course, the square root of 576 is hopefully 24. And it is. Radians per second. And of course, now we can use that first equation again, or we can just use what we learned about linear expressions. Obviously, the velocity goes like the acceleration to the first power, so our, as the acceleration times the t to the first power. So if I in fact double the time, then I double the change in velocity. If I triple the time, triple the change in velocity. But in this case, 3 to 2 is not that great of a ratio. I mean, it's the fifths for music, but it's just not that great. So it's not very good to use. But you can see that I do in fact increase my velocity by 2 meters, or excuse me, by 4 radians each second I'm traveling. So instead of 24 radians per second, I expect it to get 28 radians per second. So omega final is going to be 28.0 radians per second. And if you actually plug that in, obviously you'd see you get 20 plus 2 times 3 seconds. Ooh, no, that's wrong. Sorry, it shouldn't be 8. It should be 26. Sorry about that. Good thing I did that. To check my work, because I just made a careless error for no reason. So that's 26.0 radians per second. Y'all can, watch this video or go back and see what the crap I just said and why that led me astray. Obviously, I made a boo-boo. That's not appropriate. But anyways, the final velocity in this case is 26 radians per second. And again, that's angular velocity. There's the other answer, 24. 69 was the second part, and 44 was the first part. Anybody have any questions on that?
Yeah, I have a question.
Yes.
We use the theta equals 1/2 alpha t squared.
Mm-hmm.
Was that one of the numbered equations from earlier?
It was like the last one I did. So equation 6.
Okay. Thank you.
No problem. So we only got like 6 minutes left or 7 minutes left. So let me jump in. We've sort of covered the dynamics portion of the rotational motion, or circular motion, I should say. The dynamics portion is, I hope I said kinematics, but I'm thinking in retrospect, I just said the word dynamics by mistake. I got Ayaka's message. So anyways, what we did cover just now was the kinematic section, and now I'm going to cover a little bit of dynamics just so you guys will be ready to start some stuff. So first off, we need to find the analogy to Newton's second law of motion. I've already said it to you out loud. So it was Newton's second law of motion said the summation of the forces is equal to, there's 2 ways you could say it. You could say it MA, actually there's multiple ways, or you could say the summation of the forces. Again, these are external forces, and it's got to be the total sum of all the forces. This is equal to M dV dt. That's another way of saying it. Or you could say, the way we learned last chapter, the summation of forces is equal to dP dt. All of those are Newton's second law of motion. We could call this equation G, we could call this equation H, we could call this equation I, right? Well, the rotational analog, I will tell you the symbols are the summation of the torques is equal to I times alpha. And that, of course, would be equation 7, I think. Oh, that's all right. We jumped beyond 7 because we did those 2 equations that didn't have a linear analog. So this is equation 9. Or we could say the summation of the torques is equal to I times d omega over dt. And that would be equation 10. Or we could say the summation of the torques is equal to dl dt, where we use L for the rotational analog to momentum. It's called the angular momentum. That's what L is. So I equals moment of inertia. Again, that's in physics world. And that's defined as the summation from I equals 1 to N, say, of M sub I R sub I squared, or the integral of R squared dm. Okay. And then there's also L, which is called the angular momentum. Which is defined to be, there's a couple ways you could define it, but R cross P is one way you could do it. You could say also its magnitude is I times omega, because just like P was equal to MV, M's analog is I and V's analog is omega, so you'd expect that as well. Okay, you got 2 minutes left in class, so that warning is. And the direction, by the way, is given by by a right-hand rule. As you can tell by the left definition, R cross P, because cross products, remember, use a right-hand rule. That tells you that. Now, the other thing is, what is the torque? Well, it turns out the torque in vector form is R cross F, but you could say the magnitude of the torque is R times F times the sine of theta, which is the same thing as R perpendicular to F, which is the same thing as R times the component of F perpendicular to R. Okay, so all those are the same thing as well. So we now have a lot of new kinematic expressions that we learned up through equation, what was it, equation 8, but now we also have some dynamic equations, and those dynamic equations involve these variables, but they're going to have a little bit weirder properties with regards to the vectorness of them. So for instance, a vector rotation is not commutative, or excuse me, I shouldn't say commutative, I should say, well, the order of application matters when you're doing rotational vectors. So if you rotate something about the y-axis and then rotate it about the z-axis, you get a different answer than when you rotate it about the y-axis followed by the z-axis. So, or excuse me, I said that backwards. But if you first rotate by the y-axis and then by the z-axis, you get one answer. But if you rotate by the z-axis and the y-axis, you're probably going to get a different answer. So that's a little bit of weirdness. Your book talks about that a little bit, and we'll follow up with this next time. Class time is over. You guys are free to go. I'll wait for the last person to leave. And thanks for coming. And I will see you guys Wednesday. I'll put the chapters up today as well.
Thank you, Professor.
Thank you. Appreciate y'all coming.
See you Wednesday.
See you then.
Will these notes be included on your Google Drive?
Yes, I put them on there almost immediately afterwards.
Okay.
And the video will be up on the YouTube channel.
Okay. Also, are we able to do like a review session from our midterm?
I know, but there's an announcement going to come about that. I'm trying to work out some details about what I'm going to do. So I don't have that ready yet, but there is something coming on that. So, okay.
Okay, so like, I was wondering if even individual office hours. at
Yes,
some
I
point-
can definitely work with you on an individual case, an individual person case, one problem at a time or something like that. That's not a problem.
Okay, so I might try to do that.
All right. And also during lab, remember that's one of my office hours. So that's acceptable.
Okay, thank you
Right.
so much, and
problem.
sincerest condolences to you, sir.
Thank you. I appreciate
Thank
that.
you for class. Yeah,
Yeah, I
have a
appreciate
great
your
rest of your day.
contribution to class today. It was nice having somebody to answer me. Of course, everybody's doing a lot better than I thought too. I just won't pay attention to the chat. So have a good one. Bye, Michaela.
You too. Thank you. Have a good one.